Good evening, everybody. Can you hear me all the way there? Thank you. So good evening, everybody. Hope everybody had a chance to attend the keynote session today morning. The new way to cloud? Yes? Awesome. Super excited to be part of this journey. We all, as an industry, a community, can shape, deliver, and influence the new way to cloud. What we have in store for you folks today is in the next 45 minutes, we will partner with this presentation lineup between myself, I'm Raj Gulani, Director of Product Management in Google Cloud, along with Peter, Group Product Manager in Google Cloud, and Noah Goldman from Uber, in addition to our engineering leader, Robert Love, who's in the audience here as well. Now, what we have in mind for you for the next 45 minutes is effectively playing out what is global front end, the overview and differentiation, what is the extensibility and the programmability that this solution offers to you as a customer, the new deployment architectures enabled with new innovations, and then we hear from Noah in terms of how has Uber benefited by deploying GFE is what we have in store for you. A bit of trivia here. I will not disclose upfront the section on AI, ML, powered GFE. Okay? Instead, I will let the mystery unfold as we progress through the session. Okay? Now, when we think about global front end, what effectively this is listening to our customers and their requirement for a solution natively available from Google to deliver and protect internet-facing apps and content, comprehensive of global load balancing, high-performing cloud CDN, as well as protection from DDoS, web, API attacks, advanced fraud, bot and fraud. The solution is based seamlessly in consuming cloud CDN, cloud armor, and cloud load balancing built by the same team, the same infrastructure used by Google to serve its billions of users in delivering search, YouTube, and mail. Now, in the context of continued innovation, Cross-Cloud Network was launched last year at Next. The continued innovation in Cross-Cloud Network has led to GFE now being able to serve you as our customers for origins outside of Google. You could have your origins in another cloud, on-prem, or in other locations in your data centers that now can be served with GFE with private and public connectivity options. The one that I'm most excited about is the app connector in terms of a connectivity option for you as our customers. And my colleague Peter will speak a lot more about it in the What's New in GFE section. Now, let me explain to you the investment that Google is making in our global network and why this is relevant to you as our customers. Now, the Google Cloud Network is available in 200 countries, in 40 regions, 121 zones, and 187 network edge locations. Why this matters to you as a customer is now you can deliver differentiated, sustained differentiated products and services using our Google network. So it is in the benefit of you as a customer. Now, when we think about building the network, building the products, building a solution for you, we also want to share with you some of the proof points to meet your expectation of Google's global front end, primarily around performance and security. So when you think about performance, the lowest possible latency is a hallmark of the highest performing CDN, which directly relates to your end user experience, benefiting you in all the e-commerce transactions happening on the websites delivered on our CDN. And then when you think about security and DDoS, Google protected our customers with the largest DDoS attack reported on the planet, the one that's accounted for. 398 million requests per second. DDoS was, protection was offered to our customers. What is more interesting is if you think about the trends in these DDoS attacks, right? You see that the DDoS attacks have increased by 10x in 2 years between 20 and 2022. Another 5x in 1 year between 22 and 23. Effectively a 65x increase in DDoS attacks. And that's what we have signed up to protect our customers against, right? Now, when we're able to achieve this performance and security is purely because of Google's commitment in R&D for our routing algorithms, caching techniques, and continued investments in Cloud CDN, Cloud Armor, and Cloud Load Balancing. Here is another proof point on how our innovative product architectures play in the benefit for our customers. Now think about delivering simplicity. Simplicity is very complex to deliver. Our simplified architecture with global plus local load balancing makes our customers more successful because of low latency, low load on the origin, and cost-efficient solutions. You think about a global Anycast with global network, less regional infrastructure, benefits our customers with an availability of 99.9%, 20% lower latency, and up to 40% TCO savings. Now let me present some of the product features of the GFE solution. And we can start with the Cloud CDN here. Now when you think about Cloud CDN, this is effectively meeting a customer expectation in terms of performance and security. Now, when we talk about extended caching, as an example, this is to serve our static assets that rarely change, like CSS files, JavaScript libraries. This leads to increased performance, reduced load on origin, and optimized cost. Now, content authentication, as another example, effectively offers maximum control to who can and cannot access your origins with URLs, signed cookies, as an example. This prevents unauthorized access and mitigates hot linking. Now, if you take the journey for the next product, which is around WAF and DDoS, this is effectively meeting our customer requirements in terms of delivering security performance at scale. Now, when we talk about mitigating infrastructure DDoS, TCP sync floods, amplification attacks, IP fragmentation, allowing block traffic and rate limiting with IP, based on IP, geo, and custom match parameters, this is all packaged to you as part of a single product. And taking this further in terms of the advanced capabilities on our load balancing product, and now enabling you to have your workloads not in Google Cloud alone, but across the cloud and on-premise, is what is available to you currently shipping in terms of these capabilities. Now, when we think about this, right, is we've seen many customers use our load balancers for VMs and containers workloads in Google Cloud. But we're also seeing an acceptance and adoption of having the workloads outside of the cloud. And that would be another proof point that you will hear from Noah as he talks about Uber's use case in terms of how we are supporting hybrid and multi-cloud deployments as well. Now, with this overview, I will hand it over to Peter to talk more about what's new in the global front end. Thank you.
Great, thanks a lot, Raj. So I wanted to dig deeper first into the programmable aspects of our global front end. First, something new that we're announcing at the show is our new service extensions capability, which is going GA. This really opens up end-to-end the web data plane to make it programmable. We're talking a lot about the global front-end load balancer here, but this same integration interface exists with the internal application load balancers, media CDN, and coming soon to our cloud secure web proxy and cloud service mesh later this year. So what it means is customers and partners can create and integrate once and leverage that across a broad set of web data plane products. And we have hooks to allow for a wide range of programmability for web requests and responses. Some examples are changing origin routing, adding security services to inspect and protect, the ability to actually manipulate the requests themselves, like headers, or even get in there and mess around with the HTML, so it makes it easier to integrate new services. One of the new integrations is actually from Google. It's Apogee, who's plugging into the load balancer so they can watch traffic going in and out to look for shadow APIs and help people understand the API traffic going through the load balancers. Plus, we have a number of security and experience partners that are building integrations. On the security side, we have Broadcom, who's got a Symantec DLP integration so they can look for data exfiltration. Imperva, who's doing a WAF offering for GKE clusters. Human, who's doing bot management. Palo Alto Networks, that's doing enhanced web security. And Traceable, who's using it for providing API protection capabilities. They're all building service extensions that'll help inspect and protect web traffic going through the global front end. And then on the experience side, we have Datadog, who's doing an integration for easier analytics. Qt, who's doing an advanced waiting room capability. And then we have worked with Cloudinary and Nagra, who've hooked into the media CDN to do asset optimization for images and videos. Additionally, in addition to all this, we're releasing a set of example integrations we'll put in a public GitHub. And we've got 5 right now. We'll have 10 by the end of the month, and we'll keep adding in there. But this will give you out-of-the-box kind of code that you can take and use as is for something like header manipulation, or you can take and extend it to do anything you want. And we'll add more over time. And then what type of session would this be without some sort of generative AI mention? So we're excited to be announcing new innovations around load balancing and AI workloads. AI workloads are quite a bit different. So you look at a web request, it's like 1 second request response max, right? Normally you want it in milliseconds. But with generative AI prompt requests and responses, this can take 20 seconds. It can take up to a minute. And these requests on the back end, instead of web requests where you can maybe parallelize a bunch of them on Xeon or something like that, they tend to take up 100% of the GPU and TPU resources on the back end. So we need to do load balancing differently. LLM platforms do load balancing a little differently. They use queues for prompt processing, so they maintain like a queue depth. And what we've done is we've enhanced our cloud load balancers to actually consume information from any LLM about the queue depth, and we'll use that to actually load balance requests across your GPU and TPU-backed infrastructure. So you can give people a lot better experience. You get the prompts coming back faster, the response coming back faster, and also better and more even use of the infrastructure, which can be expensive and limited right now, given everybody is building all these great AI systems. And then we've got a bunch of additional enhancements around dealing with Gen AI type traffic, where we can optimize traffic management and failover across different regions. So let's put some of this together with a quick demo. In this case, what we've done is we've integrated our load balancer using a service extension to Cloud Vertex AI. And what we're going to do is when we send an incoming request, you'll see some text or even an image. We're going to send that over to Vertex AI to identify it, and then the load balancer is going to route it to different submodels that are sort of specialized for one type of image or object or another. So like if it was a picture of a pizza, we'd send it to the circle model, which is optimized for that kind of object. So let's see a quick demo here from Neil on my team.
To start the demo, let's use a text prompt with word box embedded in a request. AI responds with the instructions telling the load balancer which backend to forward the prompt. This backend stores the request and sends a response to the client. The stored item counter on the rectangle backend has gone up by 1. Now let's try an imaged prompt. In this case, we'll choose the image of a ball. Once again, AI instructs the load balancer which backend to forward the image, to the circle backend in this case. As expected, the circle backend now stores the prompt and the counter has incremented by 1.
Great, so that's a quick example of what we can do, and we're going to put this example, it's real, it's live, in our GitHub repo as well, so you can play around with it. But you could use this for quickly, sending requests off to a preprocessor model that would then, maybe you want to optimize costs, right? So you don't have to send everything to a very expensive model. You can have different models, and depending on what people are putting in the system, you can use the load balancer to route it to different places. We'll also put a longer version of this up on YouTube as well. So next, I wanted to spend a few minutes highlighting what's new across the global front-end solution. First, let's start with new innovations around DDoS and web protection with Cloud Armor. First up, we have CloudArmor Enterprise, which is the new name for our most premium tier. This is the one with the ML-based adaptive protection system. That's the one that was able to help protect against that massive DDoS attack. It also includes Google Threat Intelligence, and for our annual subscribers with premium support, you get access to our DDoS response team. Those are the same people that actually help protect DDoS properties, or Google properties like maps and search from attacks as well. We've also, in addition to the annual model, we've just introduced a new pay-as-you-go model for CloudArmor Enterprise. So this lets you more easily consume it, in addition to still having the annual plan. We've also enhanced the adaptive protection system. That's the ML-based system that'll model traffic and find and help block attacks. What we've done is add per-service traffic models, so you can actually tell us that part of your site or part of your API goes to a specific microservice, and then we can create more granular models to understand the traffic and do a better job of finding and stopping attacks. And then we've also continued to invest in our API protection capabilities. So we've recently added support where we can actually look into GraphQL API traffic and inspect and protect those types of requests as well. Now let's talk about what's new in web performance. We recently released expanded support for dynamic compression in our cloud CDN. So this uses gzip, and broadly it'll automatically identify what the browser supports and compress text, fonts, JavaScript. It lets us compress this stuff 60 to 80% for faster page load performance. And then new at Next, we're announcing a new partnership with Catchpoint around performance observability. They have a fantastic service that provides global visibility to web experiences, anything from a single object to a multi-page complex transaction. And as part of this partnership, Catchpoint's actually going to offer a free trial of their solution, plus, more importantly, access to their performance experts to help you measure the performance of your existing solution relative to Google's global front-end solution. If you're interested in the free trial, you can email them, or we actually have a few folks from Catchpoint here. They'll be up at the end of the session if you want to chat with them about their solution. And what we did is we actually took their product and we took the feature I just talked about, dynamic compression, and this gives you an example of what it looks like. So they have probes all over the world, so we took a bunch of measurements showing kind of what performance looked like before we turned on dynamic compression, then we turned it on. You can see a 70 to 90% improvement in performance, and that was based on a 70% reduction in object size. So you can offload that to our edge. We'll automatically, as I say, will compress for broadly or gzip, depending on what the endpoint supports. Next up, our global load balancer. So it's responsible for HTTPS traffic termination, and then it coordinates communication with backend infrastructure all over the world, if it's in our cloud or other places. We're announcing at the show the ability to access web origins privately over the public internet. We already support accessing origins outside of Google Cloud using FQDN, an IP address, or you can actually also use HAVPN. But that requires opening ports from the other location out to the public internet. There's ways of securing that, but for some folks, they have rules against any open ports to the internet. And so now with our app connector technology, you can privately access these origins with no open ports. We have an app connector agent that goes in VMs or containers. They'll boot up, and they'll actually connect back out to a gateway service that's running in Google Cloud. And then we create a secure tunnel, and we'll map requests to your origin over that existing secure tunnel. That's in gated preview now, so if you're interested in that, you can come up after the show, or you can contact your field sales team, and they can help you get access to it. And then we're announcing the release of our CICD automation toolkit for protecting and delivering internet-facing applications with our GFE solution. So that integrates CloudArmor, Cloud Load Balancer, and Cloud CDN into popular CI/CD platforms. So we have support for Jenkins, GitLab, and our own Google Cloud build. And it's an opinionated approach with best practices built in across those three products. So we went around, took all our best practices from our field, our customers, our professional services folks, and we baked it in here. So it's got all the recommended settings for delivering and protecting your web services. And then we've pre-created workflows for things like deployments of our stack plus your application, updates to both infrastructure as code for our apps or your apps plus our stuff, rollback operations across the global front end that's coordinated across the 3 products. And then we spend a bunch of time building pre-created workflows for doing canary rollouts. So it allows you to easily test new versions of your applications with partial levels of production traffic. So our new load balancer that we released last year can do a lot of fine-grained traffic control, and this is all taking advantage of that. In addition to the CICD toolkit, you can use the whole thing or you can take bits and pieces. It's designed as a toolkit. We also have a new architecture guide that has a lot of information about deployments, some of which I'm going to cover up next in the session here. So for the last part of my time, I wanted to cover a few different deployment architectures with you. I'm also going to talk about some best practices as we go through this as well. And then Uber's going to come up and talk about the architecture that they have. So first I'll talk through the most common one, which is the deployment of the global front end with VMs and containers in Google Cloud. Then we'll move on to talking about hybrid and multi-cloud. So this is when you have web origins outside of Google. We'll first talk about doing that with dedicated connectivity, where we're actually running physical fibers between our big network and on-prem or colo or even other cloud providers. And then I'll talk about hybrid and multi-cloud over the public internet. And as I said, along with covering these architectural patterns, I'll also give you a few tips, recommendations for each one of those patterns. So let's start with GCP VM and containers. Here you can see we have one or more regions running with fleets of VMs in GCE. In this case, you use something called a managed instance group behind the load balancer. That lets us scale up and down the VMs as you get more traffic. We'll scale it back down to control costs. To reduce latency, you want to have multiple regions set up, and this also gives you higher availability. So what will happen is the load balancer will automatically send requests to the closest region to optimize for performance. And if a region goes down, it'll automatically fail over request to the next closest region. So we have a fantastic private network. Raj was talking about that. So we require a lot less regional infrastructure. You can get the same levels of performance without having to have 4 different regions in the US. You could just do East Coast and West Coast. So there's a big hard dollar TCO savings as well as reduction in operational complexity with that. For container infrastructures, you'd use GKE, of course. You'd actually use something called a zonal neg. With the managed instance groups, the load balancer is helping decide when we should scale up and scale down traffic. In the case of using GKE clusters, you want to actually let the GKE cluster do that. It'll automatically figure out when to scale up, whether it's the cluster size or additional nodes. So you'd use a different kind of backend behind the load balancer, the zonal negs. So next up are some tips and tricks. So make sure you're deploying the latest load balancer with advanced traffic management, not the classic load balancer. That'll give you a little hint that maybe you're on the older version of the load balancer. This has all the latest features, including things like request mirroring, fault injection, header transformations, and more. That's where you're going to see all the latest and greatest features show up in the future. We still certainly have a lot of folks using the classic load balancer, but over time we see more and more people migrating to get all the latest features and functionality. For GKE deployments, as I said, make sure to use zonal negs, not managed instance groups. You want to let the GKE cluster scale up and down as needed, rather than having the load balancer do that. For GCE deployments, when you're using VMs, we suggest you use zonal managed instance groups versus regional managed instance groups. That'll provide some additional request controls. This is really useful for troubleshooting. So you can actually do things like draining requests from a specific zone, failing between zones during troubleshooting if you're trying to simulate some sort of failure. And then in all cases, I won't cover this each time, but we'd recommend that in advance you turn on health check logging and request logging so you get better observability. That's why you're getting a lot of logging, so if something comes up, it's much easier to troubleshoot. You can go back and look through the logs. And we send all this stuff to cloud logging. Next is the deployment pattern for when you use the global front end with infrastructure hosted in other clouds or on-prem. In those cases, we're always going to recommend you use dedicated private connectivity, either cross-cloud interconnect, dedicated interconnect, or partner interconnect. In these cases, you'll see 2 lines there. You'll deploy at least redundant physical network connections to your data center or your cloud provider for those private communications. In the case of the other cloud provider, you'll leverage their private connectivity to meet ours. Some tips and tricks here. As I mentioned, this is our preferred connectivity pattern for outside of GCP workloads. I'll talk about public options in a second. But if you're running a ton of traffic, this is the way that we'd prefer you to use it. You'll always want to use multiple dedicated links for reliability and performance. And then for this type of deployment, we'd recommend you use hybrid regional negs. It gives you more control over things like zonal availability and health checking. And then the last pattern for non-GCP workloads and other clouds where you want to communicate over the public internet is this one here. We've got a variety of options. We have 2 existing options plus the new app connector one that we just talked about a few slides ago. If you're using the first one, that's a regional endpoint internet network endpoint group. That's where you can put in an IP address or a fully qualified domain name of anywhere on the public internet, and we can address your back-end web infrastructure. It can be in another cloud. It can be on-prem in a data center in someone's closet at home, and we can talk to it to send the request. We can also use HAVPN. In that case, we'll have 2 VPN channels. So we provide it as a software service, a Google Cloud. You'd need some sort of VPN concentrator on your side. Both of these require you to open some ports. But the last one is the new one with App Connector, where you deploy those App Connector agents. They'll spin up, connect back to our managed service, and then all the requests get sent over that secure connection. That way you don't need any open ports from your origin environment. So now some tips and tricks for this pattern. Consider using regional internet negs when you know the location of the origin versus our global internet neg. That'll give you higher zonal availability and then also enhanced health checking. If you're using HAVPN, use regional negs versus global for the same reason. You get additional health checking. And then with all the other patterns, turn on logging. It's much better to do it in advance. Then you have all the telemetry there when you need it for troubleshooting. Next, I wanted to hand over to our fantastic customer, Noah, from Uber, to talk about how they're using the global front end in their environment.
Hi, everyone. My name is Noah, and I work on what we call the Uber Edge. I imagine most people don't need an introduction to Uber, but just as a refresher, Uber offers rideshare and food delivery services to markets and countries around the world. At any time of day, over hundreds of thousands of users are participating in rideshare, and there are tens of delivery orders being submitted per second. But really, kind of the core problem that Uber solves is connecting drivers, riders, eaters, delivery couriers within a localized area. And interestingly, this pattern kind of feels like it should be very peer-to-peer. But really, how Uber operates is all this actually happens within 2 centralized back-end processing regions. So one in Virginia and one in Arizona. So at any time of day, there are hundreds of thousands of iOS and Android devices connected to one of these regions, serving over 1 million HTTP requests per second. And the key piece that powers all of this is the GCP Global External Load Balancer. So to illustrate what's so powerful about these load balancers, let's consider how traffic would flow for, say, a user in Singapore. So a pretty classic deployment architecture, and one that's actually in use at Uber today still for redundancy, would be where we deployed layer 7 proxies in both of our backend compute regions, so one in Virginia and one in Arizona. We would then use some sort of scheme like BGP Anycast, GeoDNS, to make sure that we're routing users to the closer of the 2 regions depending on their location. So thinking through what would happen if this user in Singapore wants to use Uber, they start up their Uber app, they're going to start to search for a ride. The first thing that happens is the app wants to discover the closest GCP region, or sorry, the closest Uber region to the user. So in this case, the Singapore user would be assigned to Arizona, which is approximately 200 milliseconds away. This device will first need to open a TCP socket with Arizona. So it's going to take a full RTT, so 200 milliseconds, to establish that TCP socket. After that, because we require encryption in transit, the device will need to perform a TLS handshake, which will take another 200 milliseconds to go all the way to Arizona and back. So at this point, after 400 milliseconds, the device is finally able to send its first HTTP request. And just like the other examples, the request goes all the way to Arizona, some backend processing happens, and in the best case, the request comes back to the user after 600 milliseconds. So again, 600 milliseconds, the user has just gotten their first byte of content that they actually care about. This is kind of an idealistic scenario, though. We're not talking about perfect connectivity. We're talking about mobile devices on mobile networks, which are notoriously lossy. So in reality, it's very likely that a single TCP segment might be dropped, which would add another 200 milliseconds of latency. So it could easily happen that the 600 millisecond best case turns into 800 milliseconds, a second, or even more. So this architecture has a problem. We're spending 3 to 5 RTTs just to get the first bytes of content back for the user. A kind of obvious solution to this problem that you could probably see from looking at our previous diagram is, why don't we put our backend processing in more regions close to the user? Like maybe we put the Uber backend processing stack in South Korea. All of a sudden, a lot of our problems are solved. Maybe the RTT is 30 milliseconds, so a lot of these issues go away. Time to first byte goes down to a pretty reasonable number. Unfortunately, though, this is a really expensive process organizationally. There's thousands of engineers working across backend and product teams who will not want to have to move their services into a new region. So for us as an infrastructure team, the key here is being able to come up with a solution that we can basically drop in and improve time to first byte without needing our product teams to go in and make a whole bunch of changes. So now let's look at this flow with a GCP global external load balancer. So we're not going to make too many changes to our architecture. Basically, we'll direct users to a global anycast address, and we'll put a bunch of these Uber layer 7 proxies, kind of similar to the ones talked about in the previous slide, in a bunch of GCP regions kind of close to our users. So if we look back at our example again, our user in Singapore is going to open up their Uber app. They're going to connect to this anycast address, and they'll need to open up a TCP socket. Fortunately, because the GLB uses these edge pops that Raj mentioned earlier on, we might be directed to a Singapore GCP edge pop, which is just 10 milliseconds away, so the TCP socket is established in just 10 milliseconds. A TLS handshake also needs to be performed, but again, because the GLB is able to offload or able to handle TLS for us, it just takes 10 milliseconds to do this handshake. So in just 20 milliseconds, compared to the 400 milliseconds required in the previous example, the device is ready to send its HTTP request. In this case, the device sends the request to the edge pop, which forwards it typically over a persistent HTTP2 connection in our situation to one of our Uber layer 7 reverse proxies, in this case, one potentially running in Taiwan, maybe 40 millisecond RTT away. The Taiwan reverse proxy then knows to forward traffic to the closest Uber compute region, which in this case is also Arizona. So it takes another 155 millisecond RTT, the traffic goes there, and finally the response comes back to the user. So at the end of this process, it's taken only 225 milliseconds in the best case to get a response back through this path rather than the 600 milliseconds in the previous example. So basically, by just dropping in the global external load balancer, we're able to give a 60% reduction in time to first byte. But again, this is the best case. In a more realistic scenario, again, we're talking about mobile devices, TCP segments will be dropped in. In the previous example, this would have added 200 milliseconds of additional latency. In this architecture, though, because the GCP edge pop is so close, the retransmit time is super low, and any loss, which is, again, very, very likely in this scenario, would maybe add 10, 20, 30 milliseconds of additional latency, which is a huge benefit to users who are on potentially lossy networks. So all these benefits together allow our users in general to get searching for their ride or food orders faster, and importantly, reduces the chance that they go away, do something else, and move their money elsewhere. So I hope it's clear at this point that the global external load balancer is a really key product for us, both in terms of its low latency and high reliability. I promise I did not copy the earlier slide. This is what I came up with too. Some other GCP products that we also use in our architecture are Cloud CDN, which we do use to serve a pretty considerable amount of static content. There are obviously other CDN offerings out there, but what makes Cloud CDN so useful for us is it's super easy to turn on, and it provides even bigger latency benefits for our users. We're also users of Cloud Armor to protect Uber from DDoS attacks, which, as again were shown earlier, I can confirm are very, very real in the world. I won't talk too much about this, but one of my colleagues is actually going to do a similar session tomorrow where he's going to discuss it more, so I encourage you to go check that out. Importantly as well, Uber actually maintains its own layer 7 proxy that's running in GCP, as was shown in the previous slides. This runs in a pretty hands-off configuration on compute engine VMs, auto-scaling in 20+ GCP regions. The role of this proxy is basically to act as a unified layer across all of our edge providers, and it performs kind of common functionality like authentication, path-based routing, and request sanitization. And this is all done inside Envoy. So some of you might have heard of Envoy more commonly in a service mesh application, but actually Envoy is a really capable edge proxy as well. Among its pretty massive array of features at this point, one that's really powerful for us is the ability to build custom Envoy plugins or filters, which can kind of give us edge compute capabilities that can, in targeted situations, be a powerful tool. Some examples of things that we've done with this are implement authentication, mobile device verification, and actually implement some kinds of cool, complex dynamic routing based on our user location. When it comes to built-in features, though, we're really attracted to Envoy because it has some critical functionality that's clearly intended for large and very high reliability deployments. Some of these features include outlier detection and overload management, which have actually in the real world prevented outages for us since we've deployed Envoy. Now, I can keep talking about what we like about it, but I don't think you really need much more proof than us about Envoy's production readiness, because the new version of the GCP Global Load Balancer that we use is actually based on Envoy. So pretty strong credentials. Envoy is certainly not a silver bullet. It is much harder to configure than other web servers. I'm sure if anybody's used Nginx or similar, it's significantly more complicated. But it's become a critical component in our stack. And GCP's continued investment and contribution to the project makes us feel very secure that we can continue using it for a long time. Now, originally, Uber had this idea that we would really benefit from running our own layer 7 proxy close to the user. We kind of had this idea that we'd be able to do some complicated edge processing where we might directly respond to users. Maybe we'd be implementing our own caching behaviors, or potentially even proxying to backends outside of the US. However, as our architecture evolved and reality kind of set in, that we're really just concerned with routing traffic to our 2 US compute regions. I think to illustrate this, let's look at an example for a user in Lisbon, Portugal, who is trying to connect to Uber. And importantly, let's look at the 2-tier architecture that the GCP Global Load Balancer uses. So the user in Lisbon is going to first connect to a GCP edge POP, just like shown in the previous example. And actually, they're going to be connecting to the first tier of the GLB. We can call it the L1 GLB. So the role of the L1 GLB is going to be to determine the closest GCP region in which we're running our Uber layer 7 proxies. So in this case, that's going to be in Europe West 2. So the L1 GLB will forward the traffic to Europe West 2 to an L2 GLB, the second tier, which will then forward the traffic onto our Uber layer 7 reverse proxy, which will eventually send the traffic to the closest Uber region, which is in Virginia. And it'll all come back at the end. So what we can basically have at face value, this architecture, it doesn't really look that bad, right? The traffic, it's a little roundabout, maybe it doesn't take a super direct path, maybe adds 10, 15 milliseconds, but compared to some of our backend processing times, that's actually not a big deal. Let's consider a worse scenario, though, specifically for a user in Fortaleza, Brazil. So what we'll see here is that the presence of Uber layer 7 proxies in the South America East 1 region, so the Sao Paulo GCP region, actually attracts our traffic in basically the wrong way that we want it to go. So our user in Fortaleza is going to connect to the GLB. It'll be routed to an L1 GLB, potentially in Rio de Janeiro, which will then select, again, the closest GCP region with an Uber layer 7 proxy, which will be in South America East 1. It'll route the traffic to the L2 GLB, to our proxy, and then all the way back to Virginia. So what we can see here is that the traffic is basically going very far south, all the way back north again, and we're probably adding somewhere between 40 and 50 milliseconds of extra latency during this. So at the end of the day, when the goal of the Uber Edge is to route traffic to one of these 2 US regions, this architecture is not particularly efficient. It also requires us to be running our layer 7 proxies in all these VMs in 20 plus GCP regions. What we realized was that our infrastructure was preventing the global external load balancer from doing its job, which is efficiently routing traffic from any point in the world to one or more destinations. All those things that we kind of thought we might do, direct responses from the edge, complicated caching, just never really materialized. So because our goal is to get traffic to the US, what if we removed all of our layer 7 proxies, all these 20 plus GCP regions, and just put them in GCP regions close to where our backend compute is? So in this case, maybe in US East 4. Now, when the user in Lisbon connects to the GLB, we see the first hop is very similar, connects to the same L1 GLB in Madrid. But then when the L1 GLB is looking for the closest GCP region with our proxies, it instead goes to US East 4. The L2 GLB in US East 4 routes to our proxy, which then goes just next door to our compute region in Virginia. So you can see that this is really a good amount more direct. And oddly enough, by reducing our global presence of our layer 7 proxies and relying on the global load balancer's 2-tier architecture, we can actually reduce the latency for users to connect to our US regions. So as you can see in the simplified traffic flow, we basically can remove our GCP VMs in 20 plus regions around the world and put them only in 2, 4 GCP regions that are right next to where our backend compute is, maybe US East 4, US West 2. So as shown in our previous example, this results in better performance and, importantly, better experience for our users. But it's not just about the performance. This change also simplifies our operations by removing the need for us to be maintaining complicated deployment orchestration pipelines that roll out changes to 20 plus regions. Interestingly, we are the only team at Uber that has to maintain this infrastructure. It's actually quite complicated and error prone, and the simplification will actually save us a lot of time in the long run. So in general, this architecture is really emblematic of Uber's relationship with GCP for edge networking. Across a wide variety of use cases, GCP has already solved common problems better than even we as a decent-sized software company can. And the ability to defer more and more of our complexity to them over time has brought benefits for our users, as well as teams like mine who actually need to maintain all this infrastructure. So I hope this gives a useful insight into how Uber uses Google to build its global front end. Thank you for your time. Go.
Can you hear me? Okay. So in summary, just quick takeaways in terms of what we attempted to achieve, and hopefully you can take away from the session, is the GFE is a native, comprehensive, highly performant, extensible solution for delivering and protecting internet-facing apps and content. That's GFE. Anywhere origin support is a very, very awesome capability that will enable a lot more use cases for you as a customer. And our entire goal was here to empower you to deliver sustained, differentiated products and services. As you see from Uber's example, a 3x latency saving means a lot in terms of experiences and a lot in terms of business and the partnership that we have worked with our customers. So that was our bigger takeaway for today. I do want to request a quick reminder in terms of helping us improve in terms of our sessions, in terms of our capabilities. So if you can please complete these housekeeping requests and effectively look at some of these QR codes to kind of just keep the sessions going here. I know we were almost, sorry, one more request is feedback is very critical for us. Content, the level of content, how it is relating to your problem statements, are we addressing your requirements, is critical as we try to improve in every session, every next, if I may.